kind of have to use the microphone, I think, for the recording person, but in some respects, I'm sure I can talk loud enough so that everyone realizes people can let me know if we have a problem. My name is Lee Busby. I work at Lawrence Livermore National Laboratory. There's three of us here actually today from Lawrence Livermore. Lee Taylor and Tom Stitt, who has so graciously loaned me his laptop for this. I'm very grateful for that. I want to thank the organizers and the sponsors of the workshop for allowing me to present to this group. IREP is a very small thing. It's an embarrassingly small project in some regards, but I believe that it will give you some novel insights into the way that C and Lua and Fortran, in this case, can interlock with each other and help solve some problems of configuration. So I'll get more into the context around which IREP developed. IREP has developed over about the last 12 to 15 months. And myself, I've only been a Lua user, a Lua programmer myself for a couple of years. So IREP is pretty recent. The purpose of this first slide is basically to let you look at it and say, I think I'm not interested in that. So if anybody looks at this slide and says, hey, that's really not my interest area, I understand. Feel free. We have limited time here if you'd like to talk to somebody else. So the general idea of IREP is that it reads program input. Lawrence Livermore writes lots of physics simulation codes. I write physics simulation codes. I'm a computer scientist who supports them. We need to get data into those programs as we run. So this goes back to the earliest uses, in some respects, I believe, of Lua as a configuration language. We read program input in the form of Lua tables. We put the input values into compiled variables, structured variables that are available, in our case, from either C++, C, or Fortran simultaneously in the same program. It detects and reports a lot of simple user input errors, and it does that in a fairly automatic fashion. And we can read most any sort of plain old data. Plain old data, of course, is formally integers, doubles, strings, and booleans, and lists thereof, one-dimensional vectors of that. So that's the design space that IREP is intended to handle. Setting it up, you define a data store. I'll sometimes use the word backend. The data store is what I call a set of well-known tables that comprise the compiled structured variables that I'm talking about. So sorry, I should talk faster. While Tom is working on that, how many of us still use RCS every day? There you go. This talk, actually, I kept in RCS. How many people remember link trees of RCS? You ever used a link tree with RCS? Before CPS was invented, if you wanted to use lots of files and put them all into RCS, you put them in one place and then build a tree of symbolic links that pointed to the original source. Think this is going to happen to you again, Tom?
I turned off sleeping, so it's my battery.
Thank you. Thank you. I'm grateful. Basically, writing the back end is essentially the same as writing a set of C structs or Fortran-derived types. Fortran has changed. The 2003 standard for Fortran brought in some very significant changes. IREP depends on them and uses them, so that Fortran actually plays an essential, critical, irreplaceable part in IREP. The only difference between writing your structs or your Fortran-derived types is that IREP provides a little input language that is basically translates your structs into CPP macros. So it's kind of a very simple one line in, one line out, a dozen macros basically to do all the work. And that's it. No other wrapping, no other metaprogramming. Anybody who's done this sort of thing before understands what I mean by metaprogramming. If you have program input, somehow you have to put it into a form that can be instructive to the compiled code. Usually you have to produce some boilerplate code, so-called. Can IREP be useful to your own code? Again, if you like plain old data, and in our case, you can also add, we've given in special support for Lua callback functions in our tables. Our particular application uses callback functions primarily for initialization. So if you have a two-dimensional mesh and you want to set up an initial temperature field across that mesh, you define a function of two space variables and time, perhaps in this case, so that the program input is written as a function of x, y, and t, returning a temperature, so that the mesh details never appear in the user input, rather than x, y, and t is written in the problem space. So Lua has been extraordinarily useful to us in this capacity, in the sense that it allows us to abstract away all the details of the mesh. Defining one variable in the back end is pretty much one line of code. As I said, it works with either C or Fortran or both together, and they can share a common data store. And they do in our circumstance. This is really a critical point, that defining that data store back end doesn't take anybody who knows much of anything about the Lua API directly. All you have to do is be able to write a C struct and do it using some simple little C macros. That's really crucial, and it turned out to be crucial in our application. After that, reading an entire little table takes a line of code, and IREP itself, as I said, is almost embarrassingly small. The main 95% of the work in IREP is done by one 75-line C function. And it's quite general, it's instructive as a example of how to use the Lua C API. It was very instructive for me to write that function. And perhaps I'll talk a little more about that in a moment. Other than that, don't expect much from IREP. Okay, this slide. This one started out, the title of this one started out from 0 to IREP in 8 little hops. And the idea I have in mind here is little tiny logical jumps that you need to make in order to get from where you are now to a essentially full understanding of what IREP does and why it's set up that way. So these are all basically observations taken together from which you can make some logical inferences. Starting points. We all agree they're here today. Lua table constructors are really nice. They're concise. They're about as simple as they can be for the task that they do. And they're quite flexible and, well, I can't really say any more than that. Point 2. Every table element in a that is in a table constructor has what I would refer to as a dual representation. Take out my pointer here. Maybe I can keep my microphone a little closer. Yes? 2 representations of the same thing. Agreed? Okay? Furthermore, it's quite straightforward to write a little reader that takes this as input and produces this on the output. Agreed? You don't have to see it in principle, but in principle, it's simple to do that, to convert between those 2 representations. Now look at this one. What language is this written in? Anybody?
It's a property in this way.
No, I'm asking if you saw T.T1.A equals 3 semicolon, what language? Well, not any of them, but Lua and C. Lua and C, yes. It could appear this way if I wrote it in Lua, or if I wrote it in C with a properly set up set of structured variables. Yes? That's really all I'm getting to here. Remember, it looks just like C. Furthermore, 2003, Fortran now has structs too. It calls them derived types, and it looks just the same as C. All you have to do is replace the dot with a %, and you get exactly the same difference that means exactly the same thing, and it literally refers to the same place in memory, the same address. That's what I mean by sharing. Fortran and C share now using this ISO-C binding. Okay, this one is a hard one. And it was especially hard for me as a C programmer. I'm a Fortran programmer too, but mostly a C programmer maybe. Fortran has a statement that we colloquially call read name list. Fortran has had a name list statement since the 1960s. It got standardized, I think maybe in the 1990 standard, but in the 2003 standard, one little critical change was made to the Fortran read name list, and that is that the standards committee said now it has to be capable of reading internal files. What's an internal file in Fortran? Anybody? An internal file is Fortran speak for a string. Okay? So, since 2003, if you had a properly prepared Fortran read name list statement, a string that looks like this, what happens? Anybody got any sense of what a Fortran read name list statement can do? It can take the thing on the left-hand side of the equal sign, it looks it up, it says, do I know anything about a type named T? Well, what do you know? I do. Does T have something in it named T1? Well, what do you know? It does. Does T1 have an element in it called A? Oh, it does. What's the type of A? A is an integer. Okay. Well, what's on the right-hand side of the equal sign? It's a 3. Can I convert that to an integer? What do you know? I can. Okay, I'll take the 3 and I'll stuff it into the address of T, %T1, %A. All of that happened with one statement. Think about what you need to do that in C. Okay, that one's kind of a big hop, but not really. Not when you know what you're looking for. The C preprocessor can output either this form or this form from a single input. So at the end, we say we can read the table, turn it into a Fortran string, parse it with read name list, stuff the result into a single spot so that both C and Fortran host codes can see the values. 8 little hops. Onward. Okay, here I'm just going to pound you over the head with what I've already told you. A Lua table, the corresponding structured C data type is just a struct. The corresponding Fortran derived type, 1-to-1. Just read across left to right. They all mean the same thing, and that's really what happens. Now, here's how I write it in IREP. 1-to-1. Begin struct IRT underscore T. What comes out, if you're in a Fortran context, is this line. IRT underscore int, A comma 3. What comes out is integer parentheses C int, A equals 3. And likewise on the C side. Simple CPP macros. That's really all it is. And it only takes, a dozen of them overall. We'll do the whole job. The Lua table reader. Now, IREP is broken up into 3 pieces. There's a table reader in front that reads the table, and it produces a list of Fortran read name list compatible strings on the output. In between, there's a Fortran read name list. On the back end side, there's a set of compiled structs for Fortran and for C. So the table reader itself is really simple. It takes this as input, it produces that list of strings as output. It doesn't have to know anything at all about the back end, and indeed it doesn't. It's a Z zero knowledge front end. It has no idea whatever is in the back end of the code. All it does is take a table, produce a set of strings. It could, in principle, be written itself in Lua or any other language you like. I wrote mine in C because it was convenient to do so, but it's very simple. So, I think this pretty much repeats what I just said. The output of the table reader is a list of strings. It makes the output, feeds it to the assignment parser, which is the nameless statement, which tries to load it into the IREP backend. If there is a matching variable in the backend, everybody's happy. If there isn't, suppose the guy wrote t equals, open bracket, x equals 3. There's no x in the backend. So what happens? The read nameless statement fails. And it communicates that error code back to the front end. And the front end says, hey, wait a minute, t.x, there ain't no such thing. So as I say, it collects and recovers from a fairly large class of misspelling errors or misunderstandings of what's actually in the back end. It doesn't care what you write here so long as it all matches up with the back end. So basically, what that amounts to is that the back end is a schema. It defines a set, an infinite set of Lua input tables that might be useful and be recognized by the nameless reader. All those tables are called well-known tables. There's a read nameless statement right there. That's the C function that calls the Fortran function that contains the read nameless statement. The only other thing I'll point out here is the name list itself. Name list, IR input / table 1, table 2, all your well-known tables. Fortran is very nice to you because you may define a structured data type that contains 200 variables. All you have to give to the name list statement is the name of the top level table. The compiler symbol table knows everything about the contents of that particular structure anyway, so you don't have to name anything except the top level tables. Also, consider how you would solve this problem in some other language that didn't have read name list. You'd have to name all the variables. You'd have to effectively register the variable, telling the front end or the assignment parser how do you associate a name named X with the address of X. That's what a symbol table does, right? That's the difference between what C and Fortran do with the symbol table, if you think about it. What happens when you compile a C program to the symbol table at the end of the compilation? Anybody? It vanishes. With Fortran, when you compile a program, a portion at least of the symbol table remains in the executable and it's made available to the programmer to access so that the programmer can dynamically look up things that are known only in the compiled code. That's a big jump for me, or it was when I realized what I could do. There were a lot of times in the development of IREP over about a 2-week period when I try something out, I can call a nameless statement from C, and I can pass it a Fortran string. It worked. I can't believe that worked. I must have said, I can't believe that worked, about 10 times during that 2-week period. But it did work, and it does work, and it's completely standards compliant with all the languages. So, and it's been proven to work with the GNU compiler set, the Intel compiler set, the Fortran group compiler set, so long as you get a recent one, and most tellingly, the IBM compiler set. If anybody here, how many people have worked with IBM XLF? IBM invented Fortran. Lovely compiler, yes? No, but they invented Fortran, and they never let you forget it. The Fortran compiler certainly doesn't. All right, it has some limitations. It stores plain old data, along with callback functions in our case. There's an escape mechanism that's built in that allows you to store other sorts of things, but that escape mechanism takes a little bit of knowledge of what you're looking for and how to set it up and store it in the back end. C Fortran interoperability rules is what limits IREP to static objects. In particular, that means array sizes and including string lengths are defined at compile time. That's good enough for most program configuration, but it's obviously not good enough for arbitrary kinds of implementation. Strings, although they are stored in a standard compliant way, are not idiomatic either to C or Fortran uses. So it's kind of an equal opportunity annoyance to store a string in an ISO-C binding compatible way. Names in the IREP backend are case insensitive. So your names have to be unique up to and including case. That's really all that means, but that's perfectly sensible. Fortran is a case-insensitive language. The data store has no introspection nor bulk operations. How do you get data out of the back end into the host code? All of that is just a straightforward native operation. You reference on the right-hand side of the equal sign t.t1.a. That's the compiled variable in a hierarchical sense, and you set its value equal to a local variable. And let's see. I think I mentioned already, there's the table in the front end has no knowledge of what's in the back end. So that's a feature, but it's also occasionally an annoyance. And obviously, you need to use both C and Fortran compilers to build IREP, even if your host code is only C or only Fortran. You still need both compilers to build IREP itself. How am I doing on time?
Yes. About 5 minutes.
Okay, plenty of time. Okay, a little bit about our particular use of IREP. Multi-physics on advanced platforms. Excuse me? I'll try to finish in about 5 minutes, I think. Multi-physics on advanced platforms code project. Over the last year, we've built a data store, a back end, containing effectively about 10 well-known tables of 400 some odd variables, and those are spread over 60 or so substructures. Just to give you a scale of what we have done. Most of those are just scalars, and the rest are just these small vectors. That's typical of physics setup codes. Most of it is just scalars. What's the starting temperature? 3.1. That sort of thing. We also extensively use, and I mentioned this already, callback functions for initializing the fields in our system. These last two are really critical to me. 2 years ago, I wrote a sort of custom table reader for each of the Fortran code and the C++ code. Standard, open up programming in Lua, look at the code, and how do you write to the C API? Lua get global, while Lua next is not equal to nil, et cetera, et cetera. What you end up with there is a very carefully tailored system to a specific kind of table, if you've ever done that sort of work before. The code in your compiled code reflects the structure of the table. We decided later on, after having written two separate ones, one in Fortran and one in C, I was then asked to go back and, oh, by the way, we'd like to bring these two codes together and make a single executable. And oh, by the way, we'd like to read a single input. So I was suddenly in the position of kind of being the broker between the Fortran programmer and the C++ programmer. Each of them wanted to try things out. Each of them needed to negotiate what are we going to call things in the single input. And I was the bottleneck. So I had to invent some way of painting myself out of the picture. And IREP is what I did to do that. After IREP was done, all the back end has really been written by the Fortran, by the code physicists. That's what we call them at Livermore. I'm a computer scientist. Code physicists are people who have PhDs in physics but still write the code. The principal investigators in this case. They did all the work of negotiating what the back end ought to look like, and they did all the work of putting it out there. Sort of remember Larry Lessig commenting to the effect that code is law? It was a very good example of what he was talking about here, because by creating the back end themselves, they could agree upon a a specific instantiation of the way that it was going to work without having to go through me. So I worked myself out of a job, and it was a good one. This slide is really only present to show you what sort of real input looks like. That's a real input for a back-end table named initial conditions. And this slide is real input of, this is pure Lua, how you would read some data from a Lua table into that back-end. So I don't think I'll dwell on that. Rather, I think I'll jump to this point to see if anybody has any other questions or would like to have any more about the context. Yes,
Questions?
in the back?
No, just seeing you have like 5 minutes.
5 minutes? Okay, 5 minutes.
A quick question. You talked about validation of error. What about missing input? How do you make sure that all the fields are initialized?
Missing input may be, of course, a desired thing. You don't have to give all input. All the back-end setup includes a default value, if you remember from the slide. So you can set a default value in the back-end. Then your host code has a couple of ways of deciding. If the set of acceptable values for a given element is, say, positive integers, you may set a default value of -1. Then your host code can look at that value, and if it's -1, they know that the table didn't have any entry for that element. That may be fine, or it may not. So there are certainly categories of semantic errors, combinations of variables that you can't handle automatically. But spelling errors or just putting something in the wrong table, that sort of thing is, turns out to be a big fraction of user input errors, and those are all caught automatically for you. And that's great. Other questions? Over here?
So am I correct in understanding that when you create your table in Lua and you read the configuration, you go with C and you iterate over that table in order to set your C structs and Fortran, whatever, as opposed to using something like metatables to set it in real time to the same memory address?
That's correct. Mine is really dumb, simple. It just does a tree walk over a table. It starts at the top, walks on down. Every time it hits a piece of plain old data, that's the leaf nodes in a Lua table, if you think about it, or most of the time. Every time it hits a piece of plain old data, it says, okay, the back end is supposed to know about that. It makes a string, it throws it over the wall to the read name list statement, and life either goes on or you get an error. In fact, what actually happens is it counts the errors, and at the end of reading the whole table, it says, hey, there were 3 things in that table I don't know anything about. Typically, 1 is enough to kill you, but sometimes you might want to know. Any other questions? Thank you very much.